Okay, so today's guest is Wang from the Department of Electrical and Computer Engineering of University of Virginia, and he's going to talk about generalization towards novel scenarios from algorithms to applications.
Okay.
So please.
Okay, thank you so much. Yeah, and good afternoon, and thank you so much for the opportunity to present here today. I'm Wang. I'm currently a fifth-year PhD candidate from the University of Virginia, and I'm excited to share my research on this topic, generalization towards novel scenarios from algorithms to applications. And in this talk, I will discuss how we can design machine learning systems that remain effective and reliable even when they are facing new tasks, new distributions, or even entirely new domains. And I will also highlight some of my recent works and how they can be applied in a real-world scenario. So let's start with the backgrounds of the generalization problem, starting from humans. And we know that the knowledge we learn may not cover everything in real life, but humans are very good at generalizing this knowledge to some new scenarios. For example, after we have learned the meanings of traffic signs, and even after they become old or dirty, we can still recognize them because we know the basic shapes of these traffic signs. And also, after humans learn to drive in a sunny day, they can also generalize this knowledge to some new scenarios like driving in the rainy day. And these examples illustrates that the humans are good at generalizing beyond the knowledge they have explicitly learned. But what about the machine learning systems? We know that the machine learning models, unfortunately, are still not very generalizable yet. For example, if we train this model to recognize the animals, and we can see that during training, we have the cow standing on the grass, but during test, if we change the background to desert or snow, the model will, the predictions will be different, and the model will predict camel and polar bears, which are incorrect. This is because the model never saw such combination during training, and as a result, they cannot generalize the knowledge of the cow to the test data. And at this point, you may wonder, these errors can happen because the models may be too small or not powerful enough. But if we look at the nowadays machine learning systems, if we have this a very large model trained on tremendous online data and cost more than $50 million, and if we ask this model to output an image of one hummed camel in the snow, and as you can see, the model output will always be the two hummed camel in the snow. This is because the model never saw such a combination of one hummed camel and snow during training, because according to Wikipedia, the one hummed camels only live in the desert. As a result, the model cannot output this kind of combination in the image. This shows that even if we have much larger models and we have a much larger training data set, the models can still struggle with the generalization problem. And if we want to get a more formal definition of the generalization problem, and we can say the key question is, can machine learning systems apply their learned knowledge to novel scenarios? For example, we have this model knowledge of driving in a sunny day, and then we want to develop the autonomous driving system, and we want to apply this knowledge to, for example, some new distributions. That means we need to drive in a rainy day, and to some new context. That means we need to drive in a different truck, and also for some new tasks. That means we need to drive instead of driving, we need to park the car in the parking lot. And all this shows that these are the novel scenarios. And if we can effectively generalize the model knowledge to these scenarios, we can correspondingly improve like the reliability, the applicability, and also the adaptability of these machine learning models. And these properties are very crucial when we want to deploy the machine learning systems in the real world scenario. And so these are benefits of generalization. And we want to ask, how can we achieve the generalization? And I have proposed two principles to achieve generalization. And I want to use this TOEIC example to show these two principles. As you can see, here we have trained the classifier on this source domain. And we know that the classifier does not perform well on the target domains in red and green due to the difference in the data distributions, right? And we have two principles that we can use. The first is invariant principle. That means we aim to learn the invariant features of these samples that are consistent across different distributions, and so that the classifier can still work no matter which domain it is applied to, right? And the second principle is the adaptable principle. That means we aim to adjust or adapt this model, this classifier, to some new domains, and so that the decision boundary can be changed according to this new data distribution, and so that the classifier can still work. And these are the two principles that I have been using to deal with the generalization problem. And so here in the following, I want to introduce my research progress towards the generalizability from these four directions. The first is the generalizable algorithms. So with these two principles in mind, I have developed various algorithms to achieve generalization that may be adaptable and also invariant. And beyond simply achieving the higher accuracy, I also focused on some other parts. For example, I wanted the generalization process to be more efficient so that we require fewer resources, and also to be more private so that we can protect the sensitive data, and also more fair, and so that the model performance is more equitable across different human groups. And my third direction is the generalization for science. So I've tried to apply my algorithms to these scientific discovery domains, because in these domains, the generalization problem is also very severe. And lastly, I'll talk about my vision for the generalization in the future. I want to make sure the models are more scalable and also more applicable to the downstream tasks, and also more aligned with the emerging foundation model paradigm. So yeah, in the following, I will first introduce the works on these generalization algorithms, and these are some of my works published in these two directions. And here I want to introduce this invariant optimization work on the graph structure data. And this is published in TMLR 2024. So first, we know that the generalization problem on graph structure data is very severe. The graph data is very prevalent. For example, we can model the financial transaction networks as graphs. We can also model the social media, such as the LinkedIn, as the graphs. But we also know that there will be some distribution shift. For example, for the financial transaction networks, the distribution shift can be caused by different banks and also different transaction periods. And for the social media networks, the distribution shift can be caused by different regions or different universities of the users. So also, to deal with this kind of distribution shift problem, we need to formulate the problem here. So we aim to train a model on these multiple source domains, and we want to generalize the knowledge to the multiple target domains. And in this example, we consider each graph as a molecule, and the distribution shift is caused by different scaffolds, which are the structures of the molecules.
On your previous slide, financial transactions, what type of financial transactions are you doing? Just give me a couple of examples.
Oh, okay. So in our data set, we use for example, the Bitcoin transaction. It's like each edge will be a transaction among two users. Thank you. Yeah. And this is like a problem formulation. We have multiple source domains and multiple target domains. To deal with this, we aim to learn the invariant features, right? Because these features are consistent across different distributions. And if we can use this example to illustrate what are the invariant features. So imagine we have a image classification task, and we have trained this model. We know that the model can learn invariant features, which are the shapes of the animals, and also some variant features that are the backgrounds of the images. And if we can only use the invariant features as the model input, that means the model is very robust to distribution shift, right? Because the model only focuses on the shapes of the animals. And this is to learn the invariant features on the image data. But if we extend this idea to the graph structure data, we know that this can be very challenging, because it's difficult to identify the distinct invariant features due to the complex graph structures. And for example, in the prior works, we are given an input graph, and we aim to extract the invariant graph from this input graph. But this input graph contains both the correlated and invariant nodes. And if we only use the invariant graph, that contains the invariant nodes, this can cause the loss of information from these correlated nodes. So that means this can cause information loss if we extract these invariant features. So to deal with this problem and preserve the information, we resort to the information theory. And how can we use the information theory to deal with this? So here we propose this optimization objective. So given an input graph, we aim to run an invariant graph, but we want to use this invariant objective for optimization. This is based on the information theory. So the first, we want to maximize the mutual information between the invariant graph and the label y. So the mutual information is about how much information we can obtain about y when we observe the invariant graph GC. And after maximizing the mutual information, I also want to make sure the learned graph, invariant graph GC is independent of the domain D, so that it can learn the invariant information. But the question is, how can we optimize this objective? Because we know the calculation of mutual information can be very difficult. To deal with this, I have derived this theorem. So by introducing a latent causal variable C, I have transformed this invariant objective into an evidence lower bound, which contains the following terms. And with these terms, we can enable optimization. More specifically, we call this objective the generative risk minimization, because we use a generator framework. So given an input graph, and we first encode it into a latent variable Z, and then we decoded it into the invariant graph GC. And this GC will be used for the classification as the input to the classifier. So we aim to optimize this objective, GRM objective, to optimize our generator. This is why we call this GRM.
This one, can you go back? So this, you're calling the invariant graph, so like this objective you have, mutual information between GC hat and Y, right? Y are labels.
Yeah.
And then what does it mean? GC hat perpendicular D, what does it mean?
This means
That, yeah.
that the GC is independent of the domain D.
How do you quantify domain? What is D exactly?
It's the different domains. This can be the source domain or a target.
Data set. Is it a?
Yeah, we consider it as a data set.
So in this one, like this
So
lower
what
bound you
is-
have here, so what is this saying? Given G and Z, what is Z again?
You mean the G?
Z. Yeah.
This is Z is the latent causal variable.
Okay, so you have the graph G, definitely with Z, you want to come up with GC hat, right?
Yeah, yes.
So that's one term, and then other term is given D. Now D is like latent variable for the GC hat or something? Or-
Yeah, yes.
And so then you are doing this thing QZ and PG of Z. Okay, can you explain what are those terms? Like why do you want to use these? What does your theorem say about this?
You mean all these three terms?
Yeah.
First, like just, my math follows me about what GC and D are as objects, and how is it possible that operation even applies to them.
What do you mean operation?
How would you
And
calculate the
independence, like, I mean, independence applies to probability distributions, right?
Yeah.
But D is not a probability distribution. What is it?
We can consider this as a distribution, probability distribution.
So you define your domain as a probability distribution.
Yeah.
And your GC, can you tell us what is GC?
This is the invariant graph, invariant features we have to run.
So I assume that's also a probability distribution.
Yeah.
And can you give us an intuition of what is it exactly?
It's like a graph, but it can also be a distribution of different graphs.
Well, it better be a distribution if you apply the independence on it. What does it mean that it's independent?
That means
I know probability wise what it is, but
Yeah, that means when we run this invariant graph, we don't want to make the domain has the influence on this invariant graph.
So you,
I mean,
you have-
casually, yes, but you are using the formal definition, yeah.
Yes, yes,
So, okay, so you want to maximize this. You want to what? What's, to find what? You want to find the GC hat. You want to find a new graph. right?
yes, yes,
Maximizing all these four terms.
yes.
And the graph originally is like a financial thing or,
Can be any graph.
okay, and invariants come in from where that you, in that case, what's the intuition of invariance that you want to do invariance with respect to what?
Respect to the different domains.
Different domains.
Yeah.
So, okay, maybe I think we give you time, just go through this. Let's continue, let's see what else you have.
Yeah.
Let me understand, okay?
Yeah. I think the objective is like abstract, but after we use this lower bound, and this
Yeah.
becomes like more the terms that we can actually.
So you have all these probabilities available, you have those, you know how to compute P and Q and all those things, they are given.
It's not cannot be directly computed. It's very difficult, but we transform it into
Okay,
a term.
let's see what you have, yeah. Keep going.
Okay.
Skip all these things, yeah.
Okay, thank you. Yeah, so our optimization is based on this evidence lower bound, and it has three terms. This is a generator framework, and we aim to optimize this with three terms. So for the first term, this is to ensure that the given G and Z, we can get the best GC. And that means the GC should preserve the predictive information from the input graph G. And so we model this as a supervision loss. And so that we force the GC.
What are the labels in this case? Like, what do you mean by labels?
The label is the class of this input
So
graph G.
Graph is represent class 1, class 2, or something like that?
Yes.
I see.
Yeah, this is a classification task. So
And how do you start with the getting input graph? You get from some social network,
yeah,
people, their connections. And then that has, say, person X has this network and person B has another network.
yeah.
And then what is the context of different domains? So how do you say, well, you want to take the graph, input graph G, and then come up with the graph GC hat, right?
Yeah.
And that is an invariant version, different version of different domain. Yes?
It's not from different domains, it's an invariant version of the input graph G.
And invariance with respect to domain usage, right?
Yeah.
Okay,
Yes.
okay, yeah, so keep going. Mhm.
I'm trying to understand what does it mean that for a graph to be dependent versus invariant for a domain.
It's likely, for example, have a social network,
Okay.
and the distribution shift can be like the users from different regions or different universities. But when we want to classify these graphs, there are some information that is class relevant, and we only aim to extract this information, but we don't want this information to be influenced by for example, the regions or the universities of the user.
Would it be influenced by something that it's United States?
Yeah, that can be. That's possible.
Would that count as invariant or so? No?
Like here, we only consider the domain D as the variant, the distribution shift, the reason of the distribution shift. And then these regions can be like the United States or some other countries. Yeah, did I answer the question?
Maybe
You
we
gave
find
an
out.
answer, yeah. I don't want to continue.
Yeah, maybe it shows some results on this.
Show some results.
Yeah, continue.
Oh, okay, sure, thank you. And so this is a supervision loss, and we want to ensure that the GC shares the same label as the input graph G, and so that this learned invariant graph can preserve the predictive information from the input graph G. And loss is to compare the class probabilities of the GC with the ground truth label of the input graph G. And so this is the supervision loss. And second loss is the invariance loss. So we know that this is like the probability is like given D and GC, we have to learn the optimal Z. And that means we want to make sure the learned Z, which is the latent variable, should be consistent across different domains. And therefore, we need to reduce the domain influence on the learned Z. And so we design this loss as the invariance loss so that we make sure that Z is close to all different domains. So we input all these different source domains, source domain 1 and 2, input these to learn these domain reputations and make sure that Z is close to all these different domains. And so that we can reduce the domain influence on Z. And this is to learn that it's like make Z more invariant across different domains. So we call this invariance loss. If you have no questions, so the last term is about the regularization loss. So in this loss, we have these two parallel divergence terms. The first term is to minimize the divergence between Z and the standard Gaussian distribution. And the second term is to minimize the parallel divergence between the edges in the invariant graph GC and the standard Bernoulli distribution. So with this regularization loss, we have to make sure the variance of this learned Z and GC the variance should be reduced. That means their representations are more compact across different distributions, different domains. And so that this can increase the robustness of this learned Z and GC across different distributions. So this is like a regularization term. Yeah. And with all these terms, we can optimize our generator and we can learn this invariant graph GC. And we will use this GC as the input to the classifier to get the results. And so these are some experiments. So for example, the task is the drug discovery and graphs are the molecules. And the label here is the efficacy in inhibiting the HIV replication. We have these multiple source domains as the training data, and we aim to, after training, we aim to generalize knowledge to the multiple target domains. And the distribution shift here are caused by the different scaffolds. And we can see that if we use like the empirical risk minimization, which is directly train the model without any additional optimization. And also use the invariant risk minimization. This is another method used in the image classification. They do not consider the mutual information part. And compare these baselines with our method, we can see that our method can, with our GRM objective, we can achieve a much better results on this classification task.
This you can explain a little more. Okay, so you are saying you have multiple source domain. So you have the first one, X is a graph, and Y is inactivated weights, and D is scaffold. And you have several of these X's, right?
Yeah.
And each one represent what, drug? What does each graph represent? A drug or something? Or
Yeah, it's a molecule.
molecules.
Yeah.
So molecules in connection to between molecules to the graph.
In each graph, a node is an atom.
Atom.
Yeah.
And connection is
It's the
if they are related, like the valency, band, bond, or something, right?
yeah.
A molecule. It's a so each graph is a molecule, and each node is an atom. Yes.
Yes.
Okay. So they have different molecules, and these molecules come from multiple source domains. Yes.
Yeah.
And so you want to generalize those. What does generalization means? Like you want to do? Can you explain a little more?
Yeah. So because these molecules are defined by different scaffolds, and so that means in the target domains during test, the structures of these molecules will be very different from the training data. So this is the distribution shift.
So what does scaffold mean? What does it mean?
The scaffold means like the structures of these molecules. If the molecules have the same scaffolds, they will be much similar to each other.
But is the graph capturing the structure or not?
Is
Graph will capture the structure, right?
yeah, yes.
So, which means that they are different graphs.
Yes, yes. Because each molecule is a graph, and we have multiple different molecules,
There's a graph, lots of graphs,
multiple graphs.
multiple graphs. Then these are from different domains.
Yes. Yes.
And then what's the problem that given a graph, you want to classify it or something?
Ye-
What's the machine learning problem?
It's to classify these graphs.
Graph, what's the class that graph belongs?
Yeah.
And so it would work for that particular domain, you train it, but now you want to make it work for other domains.
Yes.
Yes?
Yes.
So then you take these graphs and you have somehow way to make it invariant or something.
Yeah. Yes. Across different distributions. Yeah.
I see. Okay, yeah, so you have 10% improvement of this.
Yeah. Yes. So this is only one of the data set we
Mhm.
used for evaluation,
Okay,
and we also try to use these Cora networks. So these are the citation networks, and it's like each node is a publication, and the distribution shift is caused by the different years of these publications.
yeah, maybe this will be more intuitive, right? So this
Yeah.
Cora graph is,
Yeah.
each graph consists of one author or something, or what is the Cora?
Yeah. So this is like more like a node classification task. So each node is a publication.
Publication
Yeah.
and their relationship of these publications, whether they cite or something, or
Yeah. If they are co-authored together.
co-author.
Yeah.
If there's an age, if this publication and this publication have same co-authors or something?
Yes. Yes.
Okay, so each node in this is a publication. So
Yeah.
there's a big graph.
Yes.
And what's the problem you want to solve here?
Yeah, so I want to conduct this node classification to classify each node, each publication into specific topics, like the physics or chemistry.
Cluster the cluster, the clustering, you're clustering the authors.
Node clustering is to classify this.
So you want to classify each publication with the physics or math or chemistry or something?
Yeah, yes. Yeah.
And so you have a data for this and so on.
But why are you building the nodes around co-authors then? I don't understand. I thought co-authors was to figure out, these are these camp, this is Dr. Shah and his collaborating, this is.
Yes, I think this is in the data set, so they create this data set. Yeah.
So then in this one, so what is the so you're measuring the classification of each node.
Yeah.
Your accuracy is like that, right?
Yes.
And how many total nodes you have in this graph?
I'm not sure, maybe around 10,000.
10,000.
Yeah.
And so there's a ground truth that this node at this level or something and so on.
Yes.
So you're saying your thing works better. And now what do you mean by distribution shift degree? What does it mean?
So if this entire graph contains all the publications in 1 year, so this is like one domain. And if we incorporate the publications from other years,
Oh, I see.
so this will be different distribution.
Okay, good. Thank you.
Thank you. Yeah, so this in this way we can manually increase the distribution shift degree if we incorporate more publications from other years, and so that we
ERM is what, empirical risk minimization.
yeah.
But what algorithm? What did you use? Empirical risk minimization is almost everything, right?
Yes.
Every single classification algorithm you put your hand on is empirical risk minimization, but what did you use here?
Here I only directly use the graph neural network plus a classifier, but we do not use any other algorithms. Yeah.
So all of these are using a particular graph neural network classifier,
Yeah.
which happens to be what, which one, and how big or what?
You mean each baseline?
Yeah, I don't know what is
No,
the
these are
baseline?
different methods. Let's see. So he's comparing
No, they are
different
not.
methods.
They are the same classifier, right?
Yeah, we use the same architecture, but they have different.
They are different methods, right?
Yeah.
So he's showing that ERM is one method and ARM is another method. Which one is your method?
The last one.
GRM.
Yeah.
So he's saying the GRM accuracy is better. Because the top and now the x-axis is different that can you classify, say 2025 or 2024
Okay, so
like that.
So what I want to ask though is that DRM is basically just reinforced the supervised learning, right?
Yes.
That's what we are, that's what normal supervised learning is ERM, right?
Yeah.
Okay, and you have a distribution shift degree of 0.
Yes.
How it happens that your algorithm beats regular supervised learning when there is no distribution shift?
Yeah, that's interesting. I think this is partially because we have the regularization laws, and so that we can make the learning the reputations of our graphs more compact, and so that this can be better than the baseline ERM. I think this can provide some benefits. Yeah.
Okay. Yeah.
Continue.
Okay, thank you. You can see that all the state-of-the-art generalization algorithms, all these baselines are different algorithms. They have different objectives, and they will fail with larger distribution shift degrees. But our method can still, the performance is still robust when we increase the distribution shift degree. This shows that our method is not only generalizable, but also more robust. And so the summary is like in this algorithm, we aim to learn the invariant features of the graph data with less information loss because we use the information theory based objective, and also it's we want to make sure the features are more robust against different distribution shifts. And we want to ask how can we inspire new paradigms. I think here we can say that we can use the data from all these different sources. This can be the text data, image data, or speech data, and we can learn the invariant features of all these data. These features can be like a specific concept, like some specific animals or some specific cars. This concept knowledge is invariant across different data sources. And so we can use all these invariant features to train a very large foundation models so that the model can learn more comprehensive knowledge. And in other words, we can enable the training of a foundation model from a wider range of the data sources. So this is like a new paradigm that we can apply our algorithm to. And if we look at the second research direction, this is like we want to make sure the generalization is more efficient so that we require fewer resources, and also more private so that we can protect the sensitive data, and also more fair so that the performance is more equitable across human groups. And these are some of my works on these 3 directions. And here I want to introduce the cross-task generalization in NLP. And this is published in SML 2025. And the background is that we know that the large language models are trained on a very large web corpus. But if we want to apply these models to some downstream tasks, for example, the medical question answering or multi-step reasoning, or some personalized dialogue, we know that in these applications, the data samples can be very different from the training data, and so that the performance may not be very satisfactory. And to deal with this problem, we know that we can fine-tune the large language models on these specific applications. However, this fine-tuning can be very costly due to a large model size. And the question is, how can we efficiently generalize the large language models to these new tasks? And so required to achieve generalization, another way is to use the adaptable principle so that we can adapt the models to different target domains, target distributions, right? And we also apply this principle. Here we use this the strategy called the synchronous learning for the cross-task generalization. The key idea is to use the demonstrations from this new task. These are the labeled samples from this new task, and as we use this as an additional model input. So for example, if we directly ask the large language model to predict the class or predict the label of this sentence, the prediction may be incorrect. But if we input some more domain, so some demonstrations from this new task, And this covers the labels of positive, neutral, and negative. And then the model can learn from these demonstrations and adapt to this pattern, and so that we can achieve the adaptation to this new task without fine-tuning the large language model. So that this can be very efficient. But the question is, how can we select demonstrations for adaptation? Suppose we have a pool of candidate samples, and we want for each task, for example, task 1 and task 2, we aim to select some samples as the demonstrations shown in the purple color and for adaptation of this large language model. The question is, how can we select these demonstrations? Because if we have a pool of very large pool of candidate samples, so this search space can be very, very large and increases exponentially with the number of demonstrations. And for this selection, the prior works mainly uses the similarity between the demonstrations and the queries. But in our work, we propose to use the graph structures and to select the samples that are inferential on the queries, because we know that for these inferential samples, they are more likely to help large language models to answer these queries. And therefore, we can construct a graph that contains all the candidate samples and the queries together. And on this graph, we select some candidate samples and showing the purple color as the demonstrations for this task. And the benefits of using graph here is that it's more efficient for computation and also more flexible, because we can model all different samples as the nodes in the graph. And more specifically, to select the inferential nodes, we define the concept of the node inference between two nodes. This node inference is defined as the norm of the gradient of one node with respect to another node. This can be the inference between a candidate sample and a query. We further define the node inference between a node and a set of nodes. In our case, this can be between the candidate sample and the query set of a specific task. And finally, we know that the computation of this node inference can be costly. So we further derive this theorem to provide a lower bound of the node inference. And specifically, for this node inference, we transform it into a lower bound that contains more computable values on the graphs, such as the number of shortest paths, the average node degree, and also the shortest path length. So these values are very easy to compute, and we use these values as the estimated node inference for selecting the demonstrations. So the insight here is that we transform this node inference into the more computable values. And in this way, we can have our framework. So we build a graph from all these candidate samples and task queries, and we compute the node inference on the query set. And then finally we select the candidate samples with a larger node inference on the query set. So and then we can use these demonstrations. Use this as the demonstrations for adaptation to this task. And if we look at the evaluation, so we are evaluating on 8 tasks in total. And here we show 2 examples. The first is the reasoning task to infer time information. And the second is the sentiment analysis task to predict from 27 emotion categories for each sentence. And if we look at this,
can you go back? Let's understand that. So yeah, so you're saying today is Christmas Eve of 9:30. What is the date tomorrow? So these are the option multiple choice, right?
yes.
So then what did you do? Sentiment.
This is to classify each sentence into 27 emotion categories.
Sure. Not even sure what it is. This is a different example of something, sentiment. So one is the reasoning task on data set date, and what's this a second example?
Yes, this is another data set.
And then data set. Okay, and yeah, let's go see the results. Yeah, go to the next one.
Okay. Yeah, so we compare our method with for the 0 shot, it's like we do not use any demonstrations. Random is to randomly select these demonstrations. And the 2 baselines EPR and SAIL, these are the similarity based selection methods. And we compare our method on these 2 data sets with all these baselines. Yeah. And the x-axis shows the number of demonstrations we use in this demonstration.
So I mean, if you have just 100, I mean, you can just use all of them, right? So you're saying you have many demonstration for in context learning, right? So you want to select which one to use for this particular query, yes?
Yes.
But if the number is so small, why don't you use all of them? It's very quick.
Yeah, then that's possible, yeah. If we only have a small set, we can use all of them. Yeah, but in our case, in our data sets is actually the pool of the candidate samples is like maybe several thousands.
Hmm.
So we need to select.
So these are not, the results you are showing, number of demonstration is not examples. These are, you have only 100 here, right?
Yeah,
But you are saying you have thousands, so.
it's the candidate samples. We need to select from.
Okay, here you have selected 100 to give for,
Yeah,
out of thousands.
yes,
I see. Okay,
yeah. And it's like our method can achieve best results.
okay. So this assignment paper this week, right?
Yeah, yes.
So who is presenting this work?
I asked one of another advisor. In
Professor,
another
he's
professor.
there, it's very poor.
Yeah. Yes.
Okay, good.
Yeah. I plan to go, but it had as a conflict.
Yeah, okay.
And you go to Vancouver in December for NIPS anyway, NIRIPS.
It's last year. Yeah. I see my is this week.
I know.
Yeah.
Okay, good.
Yeah.
Continue.
Thank you. Yeah, and so that's our method can achieve best result, and also it's more performance is better when we have more when we use more demonstrations, and this means our method is more scalable. And also we want to consider the efficiency. That means for these methods, baselines they need to run the channel encoders to run the similarity between demonstrations and queries, so that they need to have the training time. But our method is training free, so it's very efficient. And also for the inference time, our method is also the inference time is also much lower per query compared to the baselines, and also it can achieve this higher accuracy.
So why is it faster and inference time the method? What's the reason?
Yeah, because the selection process is faster.
Oh, I see.
Yeah. So they need to train the encoders, and during selection, they still need to perform some process. Yeah. So
But
yeah.
improvement is not that much, right? Just 3% or something.
Yeah. I think this because this task is like very difficult. So yeah, I can give a summary here is that we can improve the efficiency of the adaptation of the large language models to new tasks. And for the new paradigm, it's like if we have a financial model and we can use our algorithm to effectively and efficiently adapt this financial model to the downstream applications. And we only need to use a small set of the task-specific data, and so that we can enable the efficient adaptation to these new applications. This can be very efficient, especially in some cases. It's difficult to obtain sufficient data, and so this can be very helpful in that scenario. And in other words, we enable the adaptation of financial models to a wider range of the applications.
So you have done these, or this is just future work?
This will be future work.
So, okay, how many more slides do you have? Are you done or you have more?
We have one more work, but I can introduce it very quickly.
Yeah, that's, go ahead.
Okay, so this is about the generalization for science. I apply my algorithms to scientific discovery domains. And these are some of my collaboration works, because I would love the broad collaboration with researchers from different institutions. And I want to introduce this work is about to use the neural imaging data to predict human status. So we have this fMRI data, and we can predict human age or human's Parkinson's progression. And we have this distribution shift. We have the data collected from different sources, such as different hospitals, and this can cause the distribution shift because the devices in different hospitals are very different. So we have this source domain and target domain. They have very different distributions. And to deal with this, we need to run. We can run the invariant features of these samples, right? And we want to ask what is invariant across human brains. And inspired by this Nature paper, we use this real-world biological mechanism, which is the activation pathways. That means when humans are conducting some vision tasks, for example, they will have this dorsal pathway and a ventral pathway to deal with different information. Pathway is a sequential activation of brain regions, starting from one region and ending at another region, and this will traverse across the human brain. We want to use this as the invariant features. So we can formulate a pipeline as given input in fMRI data, we use a pathway learner to learn a pathway, which is a sequence of brain regions, and input it into the classifier for prediction. And we want to learn this, optimize this pathway. But the question is, we do not have any ground truth for this pathway because it's very difficult to achieve, even for the domain experts. And this work is published in AAAI 2025 as an oral presentation. And then to optimize this pathway, we design this pathway as we learn ordering score for each brain region. And then we can obtain this ranking of the brain regions on the descending order of the ordering scores. And this is that we use this ranking as the pathway and input it into the classifier. The question is how to optimize this pathway learner. And we use the contrastive strategy. So if a pathway, we sample multiple pathways and feed them into the classifier. If the outcome is correct, then we consider this pathway as a positive. And the outcome, if outcome is incorrect, we consider this as negative pathways. The optimization is to make sure the learning pathway is close to positive pathways and distant away from the negative pathways. And this is intuitive, but if we want to optimize this pathway learners, but we have these questions, how to determine the similarity, and we use this Spearman's correlation coefficient. And another question is how to enable a gradient flow, and we use this theorem support so that we can transform this optimization target into this optimization loss. And this loss involves the ordering score learned by the pathway learner, and so that we can enable the gradient flow for the optimization. And this is the contribution of this theoretical analysis. And finally, we can say that if the task is to predict human behaviors, this is a classification task. And we have this source domain. This is from a public data set. And we have a target domain. This is from the University of North Carolina, their private data set. And there is some distribution shift. And if we use this method, for example, the multi-layer classifier, and use the graph neural networks, and with our objective involved, we can achieve a much higher accuracy in this classification task.
So in this one, you have this fMRI data set,
Yes,
and the problem is what? To
classify.
classify,
Yes,
how many classes you have?
7.
7 classes.
Yeah.
Okay, and so what can you say a little bit more? What's the pathway? Can you explain a little more?
Yeah, the pathway is like a sequential order of the input graph. Of the
So you make a graph out of the fMRI.
yes,
And what are the nodes in the graph?
each node is a brain region.
And you already have detected brain regions.
Yeah,
You already know because given fMRI, you already segmented, and you have these different brain regions,
yes, exactly.
and you have a graph.
Yeah, later we transform it into a graph.
Yeah, so you get a graph.
Yeah.
And pathways that how, like this, go from one node to other node,
Yes, exactly.
and this is what, how do you determine this? The arrow, like, you have some information, how do you, the edges are defined like how?
It's defined by the correlation among the brain regions.
Okay.
Yeah.
So that's, you make a graph.
Yes,
Now pathway is what, one path, and
yes.
how does path determine like which the similar nodes will go to, like, how does it work? Why doesn't it go to the blue one compared to the yellow one?
Yeah, this is learned by our model, pathway learner. So it can go to any nodes, but we want to learn this path. It's like how it will go from one node to another node. So this is we have to learn this path with our model.
I see.
Yeah. So the learn is like we learn an ordering score for each brain region, and the ranking of the path is starting from the high scores to the low scores. Yeah, this is how we learn this path.
And so you work with your collaborator in where?
University of North Carolina, Chapel Hill, Department of Psychiatry.
I see.
Yeah.
And so your advisor was also involved in this project, or just you?
I contributed the most.
Just you yourself?
Yeah,
I see. Okay.
yeah. I found this collaboration by myself. Yeah.
Good. Yeah.
Thank you. Yeah, I also have a lot of this kind of collaboration in different institutions. I love to explore this scientific.
So this theorem you have, can you go back? Theorem. So, yeah, this is your theorem,
Yes,
and you prove it is correct.
yes, yes.
Okay, that's,
Thank you. Yeah.
okay. Yeah, so Ali, you can check it.
It's very complicated. You can't keep together.
Okay, keep going.
Thank you. Thank you. Yeah, I love to use this theoretical analysis and support for the justification of my method. And this is the explanation result. So it's like for the red and yellow regions are our identified activity regions that are ranked very high in the learning pathways. And the green regions are the ground truth regions by the domain experts from our collaborators. And we can show that our identified regions are largely aligned with these ground truth regions in the green circle. This shows that our method can actually identify the activity regions in the brain. Yeah, I'll quickly go through this generalization in the future. This is like we know that we have in the ultimate goal of the generalization is to improve the generalizability of models. And in the past decades, we have this stage 1 and stage 2, which are some models like SVM, CNN. They can learn the limitations, but they are not very generalizable. And in the stage 3, we are in this stage. The financial models like large language models are very powerful. But in the future, we will aim to further improve the model to become the artificial general intelligence AGI, which will be the stage 4. The question is, how can we achieve this AGI from the current stage? We think that by scaling up data and model size, using more data and using a larger model cannot solve this problem because the scaling law is saturated. And in the future, we need to make sure we develop more generalizable algorithms, and so that the foundation models can learn the conceptual knowledge just like the human. This conceptual knowledge can be applied to various scenarios, and this can also benefit from using more data. And it's like this is the overview. The key idea is to learn and apply this conceptual knowledge, and we can use the invariant principle so that we can learn the conceptual knowledge from different data sources for to train the data, to train the model. And finally, in the application, we can use the adaptable principle so that we can apply this learned conceptual knowledge to various tasks very efficiently, and so that we don't need to fine-tune this foundation model, and we don't need the domain experts to develop some algorithms. This foundation model can be easily applied to various tasks in the downstream. So this is like a generalizable financial model. And so this is an example of my collaboration with the National Jefferson Lab. It's like we have particle accelerator data, and we have data from different facilities, data from different periods, and they are very different in distribution. And our model should be able to use all these different data, and we learn the conceptual knowledge and use all this data as the training data. And also, in the application side, this generalization, for example, in IoT, we need to deal with the data modalities, difference in the data modality from different sensors, right? And also for the power electronics, we have the heterogeneity in the hardware. We also need to generalize the models to these different scenarios. And with all these applications, I can collaborate with different professors from across different departments. For example, Professor Damla, and also another application is like, for example, the generalization in the visual activity recognition, because the different backgrounds can be very different from the training data, right? For example, during tests, we have these different environments in the video or in the image, and these are it's like a generalization problem. We can deal with this with our generalizable foundation models to collaborate with the Professor Ulrich Shah, and also the generalization in the proteins and molecules. So these are, we can collect data from different hospitals, institutions, and we have different type of molecules. And I can also collaborate with the Professor Wei Zhang, and we have discussed the potential in our meeting earlier this day. And yeah, so these are some generalization in the applications. And these are some courses I can teach. For example, for basic level courses, I can teach the introduction to discrete structures. For higher level courses, I can teach the advanced AI and understanding natural language. And for new courses, I can also develop like information theory for generalization. I can introduce basics of information theory and also try to apply these algorithms to the real world scenarios and for this for students from different backgrounds. And thank you so much. All these works are also credited to my great collaborators across the industry and the academia. And yeah, thank you so much for listening. Do you have any questions?
Your particle accelerator here, what is like to learn on it?
You mean the particle accelerator? So this is like the label would be it's a binary classification, a good or bad. So for this data, the good means the beamline is the data is correctly generated, but the bad label is like the data is not correct. Yeah.
So you have this data from the Department of Energy?
Yeah, so I collaborated with this National Jefferson Lab. So it's a national lab in Virginia, and they provided the beamline data. Yeah.
What was the finance application you actually, like, I know you mentioned it a couple of times, but what was the actual finance?
You mean financial?
Yeah, you had a finance application, you said finance in your 2 slides, you mentioned it somewhere.
Yeah.
What is the actual application?
Yeah, so I can, this is one of my collaborations. It's this financial KG problem, right? So this is my collaboration with the MIT CCL. It's like we are dealing with the financial knowledge graph, and in this knowledge graph, there will be some entities. Entities can be the banks or some other companies, and we use this knowledge to answer some questions. And these questions are also generated from the content from a specific company, and we use this knowledge graph as like the knowledge base to help large language models to answer these questions.
So you input the knowledge graph to large language model?
Yes, we do not directly import it, but when we need to use this knowledge graph, we extract a small piece of this graph, a small piece of knowledge, and input it into the large language model.
And what's the data set with the data set for that?
Yeah, so I think the financial knowledge graph is like we generated this financial knowledge graph from companies, some materials, financial materials, and we generated this knowledge graph, and we use this knowledge graph to answer some other questions of this in this company.
And so knowledge graph is necessary, or you can just, put a query and ask the question, right?
Yeah, I think the knowledge.
Why knowledge graph is needed?
Yeah, because the knowledge graph contains information that is very specific for for example, the financial situation or some operations by this company, and so this is very important in answering the questions from this company.
And so
Are you thinking about, the graph would be action the company takes and the consequence of that action? Would that be the kind of graph you're thinking of?
Yeah, that involves this kind of information. Yeah.
So whom are you collaborating in MIT?
The Professor Julian Shun. He's associate professor in MIT CCL. Actually, last year I was a visiting student.
So which department? The
Department of EECS. The CCL is like a lab.
Yeah, it's a safe.
yeah. So did you get any paper yet with him or not?
Yeah. So in our collaboration in our last year, we had a paper published, and I'm the first author.
Where was published?
It's published in ICLEAR 2025 ICLR. Yeah.
That's it?
Yeah.
Yeah. Okay, yeah. So I'll then talk.
Yeah, we talked.
Okay. Thank you so much.